everyone. We are here to look at the intro to the normal distribution. So we are starting a new chapter. So we've done probability, but we're going to take that probability a little bit further and look at it more in terms of statistics. So what I want to do is I want to look at an example that we did in the last chapter, like a probability distribution, and then we'll go from there. So one of the examples we did in the last chapter was the rolling the die example. So we're going to start with that, roll a die. And then we're going to make the probability distribution. It's cold in the barn today, so things are not showing up super well. So let's see what other, get some good colors going on here. So remember that when we roll the die, definitely not that one. We'll find it, don't worry. We have our 6 options, 1, 2, 3, 4, 5, and 6. And the probability of each one is 1/6. So we've had that in our notes before. Now I want to draw you a probability histogram. And a probability histogram is just going to show the different x values and their different probabilities, except in this case they all have the same probability of 1/6. But down here we'll put our different x's, our different outcomes. 3, 4, 5, 6. And because they all have the same probability, we can just go to 1/6 over there. And then the probability histogram is not even going to have bars, it just has these little lines that go up here. So this is just a real easy little graph, but it's just basically a visual of what we have over here. So here it is in table form, here it is in graph form, same thing. Now, what I want you to notice is that if you were to connect, or kind of sketch the shape here across the top, what we end up with is a perfectly uniform graph. So this graph is most definitely uniform. You can't get more uniform than this graph. And the nice thing about that is because it's uniform, the shape we have there, the shape that's made is a rectangle. Rectangles are nice to deal with. That's why we're using this example. So now we've got this guy. Now this is the uniform graph. We're not yet at the normal distribution. We're getting there. So what I want to do is I want to shade in a portion of this graph. Okay, so I'm going to shade in that much. And because it's a rectangle, I want you to find that shaded area. Okay? And like I said, because it's a rectangle, we should be able to find this. So the area would equal the length of the rectangle times the width of the rectangle. So it looks like we've gone 2 units over, and then we've gone 1/6 up, which means the probability would be 2/6 or 1/3 if we reduce. Or I'm sorry, not the probability, the area. The area would be 1/3. Now, though, I just kind of gave it away there. Really what we're going to do is I want you to go back over to this problem, or just think about this in general. If I wanted the probability of getting a 1 or a 2 when rolling the die, okay, a 1 or a 2, wouldn't that be 1/6 plus 1/6, right? 1 or a 2, which is 2/6, which reduces to 1/3. So over here in the table form, we were able to do a probability using our probability rules, and we got 1/3. Over here in the graphical form, I asked you for a shaded area. We found that shaded area, and we got an area of 1/3. But graphically and tabularly, they're equal to each other, aren't they? They represent the same thing. So what we end up with from this graph is that the probability can be represented as area. Probability and area are basically the same thing. So we can definitely make a note of that, and we can say area under the curve. Wait a minute, where are you going? Hold on, everybody. Where are you going? No, sit down. Sorry guys, I got two little ones here. So area under the curve represents probability. Area under the curve represents probability. Okay. And you can even see that a little bit more as looking at the whole entire graph. If you take the whole entire graph and you look at the area, so that would be a length of 6 and then a height of 1/6, we get an area of 1, don't we? And basically the probability of rolling the die and getting something between 1 and 6, isn't that going to be 1 or 100%? So it's very true that this area and this probability are the same thing. And that's really important because as we've seen in the past, in statistics, they use a lot of graphs. So if we're using graphs, we can find area. Now here's the thing though, this guy is the nice example because it's uniform. The other graphs that we've been looking at, have they been uniform, or have we had some bell-shaped graphs and some skewed graphs and things like that? We have. So we've got a little bit of an issue, and that's where we're headed. So now we're actually ready to look at the normal distribution. So let me get rid of this. So the normal distribution is just another name for our good old bell-shaped curve. So the normal distribution just means the bell-shaped curve. And honestly, it got the name normal because it's what we normally expect to see. So the statisticians would see the bell-shaped curve and they go, oh, look, it's another normal curve. Oh, look, there's another bell-shaped curve. That's the norm, the norm, the norm, the norm. And so it became the normal distribution. Okay? Now, the normal distribution, we have seen before, but we're going to draw this a lot of times from here to the end of the semester. So it looks something like that. Remember that the idea here is mu is in the middle, right? And if it's a perfect bell-shaped curve, we should have some symmetry and all sorts of stuff that go with this graph. The one thing we don't have, though, is an easy way to find the area. It's not a rectangle, is it? So some things to think about there. Okay, so let's look at what we call the properties of the normal curve. Or the normal distribution. So these are just some things that we noticed just from looking at this graph. So the first thing we noted was that the mean was in the middle. So we say the mean is in the middle. The second thing I want you to notice is that for this guy, notice how my graph floats above the axis. Notice how it does not touch down on either side. So the graph floats above the axis. And the reason for this is to take into account that we don't know about outliers. If we were to take our graph and just end it like that, then what we're saying is that we know for 100% sure that there is no outlier on this end. But unless we have all of the data, can we be that 100% sure? We can't, can we? So we leave it floating just to see if there's an outlier out there. The third thing we notice here is that even though my graph might not be perfect, the graph should be symmetrical. So the graph is symmetrical. The fourth thing that we want to note, and you can't really see it from here, but go with me on this one, is that the area under the entire curve equals 1 or 100%. So the area under the curve is 1 or 100%, depending on how you look at it, either in decimal form or in percent form. And then using these two guys together, 3 and 4, one thing that does come in handy for us is that if the whole curve is 100%, if we're just looking at half of the curve, since it's symmetrical, that should be 0.5 or 50%, right? The area to each side is 0.5 or 50%. Okay, so those are our basic go-tos when we are looking at the normal curve. Again, the mean in the middle, the graph floating, the symmetry, and the area underneath. So let's say, I'm gonna write the same thing, but I don't want the little mu on there this time. So let's say that we're given a normal curve. And this time though, like in the last example, they're giving you a portion of the graph that is shaded. Okay, so just like in the last example with the rectangle, where I shaded a part of it and asked you to find the area. Okay, what if I did something like this? I give you the graph, I shade a portion of it, and I ask you to find the area. Okay, it's not so easy to find the area, is it? Not so easy to find the area. Because of this curve, we don't have a nice formula for finding the area. So what we would need to do, let's be clear, we would need to learn calculus. What? Sorry guys, I got kids here.
Can I get it down my notebook so I could copy this?
If you want. Yes.
What is that?
That's called the bell-shaped curve.
Oh.
Yep. Yep, so I've got a 9-year-old and a 6-year-old here learning math. Okay, so because our bell-shaped curve again has that curve, it is not so easy to find the area. This would be a calculus problem. Okay, so finding this area is a calculus problem. But the dealio is that none of you were required to take calculus to take this class. Now, some of you may have taken calculus and you know how to find the area under the curve, but that's not normal for most statistics people. They're not up on that yet. Okay, so we've got an issue here. We cannot do this with the methods that we have from algebra. It's not a nice shape, so there's no nice way to do this. It's definitely a calculus problem. So we need to take a step back and think about this a little bit more. And the nice thing about this is that the calculus has already been done for you. Okay, the calculus has already been done, so we just need to learn how to use the program that gives us the answers, basically. But in order to do that, we need to remember something that we learned back in chapter 3, I think. So we're gonna get to finding this area, but we're not ready yet. So what we need to do is remember z-scores. So remember when we were talking about z-scores, that was to relate two unrelatable, basically, examples or samples. So we're not going to use z-scores in the same way this time, but we are going to be required to use z-scores in this graph, or in this example. So z equals, and you should have this in your notes somewhere, but we'll write it again, either x minus mu over sigma, or z equals x minus x bar over s. It just depends on whether you're dealing with a population or a sample. Now, most of the time we're going to be here in this sample, but both formulas are basically the same. But now what's going to happen is that is going to change we're going to change our graph a little bit to include these z-scores. Okay. So in this example, having mu in the middle for the mean, okay, that's in the normal distribution. But this time what we're going to do is we're going to redraw the graph. And instead of putting mu in the middle, I'm going to put 0 in the middle. And then I'm going to measure out by 1.00, 2.00, 3.00. And the idea is that these are z-scores. So negative 1.00, negative 2.00, negative 3.00. So instead of living in the real world, which is where we might be over here, we're going to live in the z-score world. And this is going to allow us to use the program that we have on the calculator. Now, if this guy is the normal distribution with the actual mu, with the mean in the middle, then this guy is not the same graph, is it? It's the same shape, but this has 0 in the middle. And that means this guy needs its own name. So this guy is called the standard normal distribution. Okay, so the standard normal distribution. Okay. All right, it's raining here today outside the barn. Yep, we're having a rainy day. Yeah. Okay, now in the standard normal distribution, there's just a couple things that are different from the regular normal distribution. So notice here that the mean, we're now going to let equal 0. So it's still in the middle, but we're going to let the mean equal 0. So we let mean be 0. And here we measure with z-scores. So in this example, what I might do is start in the middle there and go out a certain distance and give you that shaded region. Okay? So it looks very similar to this one over here. But what I'm going to tell you is that this z-score is, let's say, z equals 1.27. Okay, I want you to remember that z-scores always have 2 decimals, so 1.27, okay, always 2 decimals. Now, as I said, that's not an easy problem to find the area of, but the program has already been done for us. All the calculus is already done. We just need to be able to do this in our calculator. So if we want to find that area, here I'll write it here first, then I'll show you on the calculator. We're going to use the calculator, and in order to use the calculator, we are going to go second on our calculator, distribution. And again, I'll show you this in a second. So second distribution, then we're going to go down to normal, CDF. And then we're going to plug in 0, 1.27. 0, 1.27. Okay, so let me show you how this is going to look. So if we use our calculator here, oops, I'm already there. So we'll go back to the main screen. So we're going to go second, and then distribution is this guy, second distribution, and it takes us right to this screen. Now the first 2 guys on there are normal PDF and normal CDF. Okay, normal PDF and normal CDF. We want the second one, CDF. Okay, so be clear on that. Click enter. Now it asks me to put in my lower and upper boundaries. And those are our 2 boundaries on our graph. So in our case, our lower boundary would be 0, and our upper boundary would be 1.27. Okay, 0 and 1.27. Go down to paste, boop, and then hit enter again, and we get an area. And notice that area is in decimal form, and we're always going to round this to at least 4 decimal places. Okay, so we're going to round that guy to at least 4 decimal places, which in my case, or our case, means that this area, I got 0.39795, so 0.3980. Okay, so 0.3980. Now, again, depending on what level of calculator you're using or age of the calculator, when you go to distribution and you go to CDF, some of you may get a screen that looks like this, okay? Lower, upper, and then go down to paste. Now, others of you, when you go to second distribution, or over to normal CDF, the screen is going to pop up and it's going to say normal CDF parentheses. Okay, that's what the screen is going to show you. Well, what I need you to do, if this is what your calculator is you're going to plug in 0, and then you have to use the comma key, okay, which is above the 7, and then you're going to go 1.27, and you're going to close, and hit enter, boop, and again, you should end up with the same area. So it just depends on which level, like how old your calculator is, basically. One version does it one way, the next year they changed it and did it another way. But it's the same thing no matter which way you get it. Okay? But that normal CDF, that is the program that gives you area, okay, under the normal curve. Area under the normal curve. And again, it's a calculus program that has already been done for us. We don't have to do the calculus part of this. So what we need to do is just be able to see some examples of finding different areas, the different types of areas that we're going to look at, and get into the groove of using that normal CDF. A dog just ran away with a dinosaur, so we're going to take a break.